This is not just the sound of a BLDC motor. It's the sound of a process unfolding, a sequence of steps working together to estimate the motor's resistance and inductance. In the previous episode, we explored how to calculate Kp and Ki using resistance, inductance, and the control loop bandwidth, and even how to manually extract resistance and inductance by analyzing waveforms. But now, imagine skipping all that. This time, we'll unlock a smarter way, letting the driver discover its own resistance and inductance automatically. Curious how that works? Let's dive in. Before we move further, we need to get a closer look at the two key properties we want to measure: resistance and inductance. Resistance is quite straightforward. If we recall Ohm's law, we know that resistance always affects the current flow, no matter when it happens. Inductance, on the other hand, has a more interesting behavior. When a voltage is applied to an inductor, the current doesn't rise instantly. It curves upward until it reaches a steady state. Mathematically, the current versus time in an inductor can be expressed like this. From this equation, we can get an idea of how to determine R and L. In a motor driver system, we can apply a reference voltage to the motor and observe the resulting current. The resistance value can be obtained by dividing the applied voltage by the measured current. For inductance, we can look at the initial slope of the current rise over time. However, here's the challenge. The current changes extremely fast, within the microsecond or even nanosecond range, making it very difficult to measure accurately. That's why a more practical approach is to inject a sinusoidal signal and measure the motor's total impedance. From that, we can calculate R and L, similar to the previous method using a function generator and an oscilloscope. Then comes the question, how do we generate that sinusoidal signal? Good question, because the answer is at the core of everything we're about to do. From our previous discussion, we know that through the inverse part transform, we can convert the voltage components Vd and Vq into alpha and beta axis voltages. Then, using space vector PWM or SVPWM, these alpha-beta voltages can be translated into three-phase signals that are applied to the motor. If we recall our original goal, it's to obtain parameters that serve as the foundation for the current control loop in FOC, namely Kp and Ki for the ID and IQ control loops. This means the R and L values we want must also come from the same frame, the direct and quadrature frame. For resistance, R on both the D and Q axes is typically the same, since it represents a purely resistive property. However, for inductance, LD often differs from LQ, meaning the parameters we're aiming to find are RS, LD, and LQ. Okay, so the scenario is like this. We inject a sinusoidal signal into Vd and set Vq to 0. Then we capture the current data. After that, we calculate the amplitude of the injected voltage, the measured current, and their phase difference. With that, we can obtain the total impedance of the motor. Based on the phasor diagram, we can derive the general equations for an R, L circuit. By using these two equations, we can find the values of R and L of the motor, where equals Z times cosine phi, and L equals Z times sine phi divided by omega. With this, we can get the values of RS and LD, and to find LQ, we simply do the same process on VQ while keeping VD equals 0. An important thing in implementing this method is to ensure that the motor remains locked and not moving during the measurement. Because when the motor rotates, back EMF will appear, which affects the measured current value. In addition, timing is also crucial. The PWM frequency serves as the time reference for both the injected signal changes and the current data acquisition. The injected signal is a sinusoidal voltage defined as sine 2 pi ft. If the PWM frequency is 10 kHz, then T increases by 0.0001 every period. The injection frequency must be lower than the PWM frequency. The higher the injection frequency, the smaller the current amplitude becomes because of the inductive property. On the other hand, the injection amplitude should not be too large to avoid excessive heating in the motor. I have created a function in my code to generate the injection signal and read the ID and IQ currents after the Clark and Park transformations. This function is executed inside the ADC callback, synchronized with the PWM timing. Each injected voltage and measured current, both on the direct and quadrature axes, is stored in a buffer for later processing. After the injection and current data acquisition process is complete, all voltage and current data are processed through a single frequency DFT to obtain the in-phase and quadrature components. From these two components, we can extract the amplitude of voltage and current, as well as their phase difference. Finally, by dividing the voltage amplitude by the current amplitude, we obtain the motor impedance. And from the phasor diagram, we can determine the values of RS, LD, and LQ. And now it's time for proof. I will test using the same motor, but with different injection frequencies and power supply voltage sources. The goal is, if our self-commissioning algorithm is correct, then regardless of the test conditions, the measured values of RS, LD, and LQ should remain consistent. But if not, there might be something inaccurate in the implementation. After finishing data collection, I compared all the data, and the results indeed varied, but only slightly, with less than 5% difference in inductance. However, for the resistance value, it appeared that the higher the injection frequency, the lower the measure resistance became. This made me think about reviewing the measurement method. From several references I've read, most of them measure resistance separately using a simpler approach. The method is to apply a constant DC voltage on the D-axis instead of injecting a small AC signal. The resistance value is then calculated by dividing the VD voltage by the ID current in steady-state condition. With this approach, the frequency effect on the resistance result can be eliminated. After adjusting the code, I performed another round of testing. In this test, I applied variations of the DC supply voltage at 12 volts, 16 volts, 20 volts, and 24 volts. For the resistance test, I used DC injection voltages of 0.5 volt, 1 volt, and 1.5 volt. Meanwhile, for the inductance test, I varied the injection frequencies at 300 Hz, 400 Hz, and 500 Hz. If the implementation works correctly, this test should produce RS, LD, and LQ values that are relatively the same. After collecting the test data again, I obtained RS, LD, and LQ results with a coefficient of variation below 5% for all three parameters, which means the results were quite consistent. And for me, that's good enough to be considered successful. Even when compared with the measurements from the previous episode using a function generator and oscilloscope, the values were not significantly different. This proves that the self-commissioning system we developed can operate stably even when the testing conditions change. In my code, there's already a calculation that determines the PI gain for each ID and IQ current control loop. So, once the RS, LD, and LQ values are obtained, the microcontroller automatically sets the PI gains based on the predefined bandwidth. And the final step to verify these values is to test them by applying a step set point on the ID current. This is intended to check whether the current control response bandwidth matches the desired bandwidth. I'll test it by applying a 1 ampere step input on ID current and then observing the current response for analysis. Earlier, I had also set the bandwidth to 50 Hz. After analyzing the ID current response, I obtained a rise time of 6.9 milliseconds. And when converted into bandwidth in Hertz, the result was 50.724 Hz, which is already close to the desired bandwidth value. So, that's how we can perform self-commissioning to measure motor parameters independently, without any external tools. A small step toward a truly autonomous FOC system, one that can recognize its own motor characteristics without the need for external measurement equipment. Even more exciting, this method can be further developed to estimate other parameters such as back EMF, flux linkage, rotor inertia, and more. Imagine, with a smart motor driver, we're not just controlling the motor, but also understanding it on a deeper level. Thank you for watching, and see you in the next episode.